Hello everyone. Today we will be covering the topic of capacitance and dielectrics and we introduce the electric series and parallel circuits. Capacitance. Referring to figure 26.1, we can define what a capacitor is as two conductors that carry equal charges and attract each other due to opposite signs. Capacitance is the ratio of magnitude of charge Q to the magnitude of the potential difference between the capacitor. Capacitance will always be positive and have SI units of farads. 1 farad is equal to 1 coulomb over volt. Calculating capacitance can be derived by the magnitude charge Q over the potential difference change in voltage to a simplified version of 4 times pi times epsilon naught times alpha. This displays that the capacitance of an isolated charged sphere is proportional to its radius and is independent of both the charge on the sphere and its potential, as is the case with all capacitors. Dependence is only on geometry of the conductor plates, and an important example of a capacitor is a portable defibrillator. Parallel plate capacitors, where two metallic plates or conductors of equal area A are separated by a distance d, the value of the electric fields is E is equal to the Q or charge over epsilon naught times area, while potential difference is calculated by the change in voltage is equal to Q or the charge times distance over epsilon naught times area, and capacitance is equal to the epsilon naught times area over distance, in which describes that moving the plates closer together causes the charge on the capacitor to increase. If D increases, the charge decreases. Combinations of capacitors. Electric circuits all have a circuit diagram in which circuit symbols represent various circuit elements. As you could see in figure 26.6, there are 3 symbols that represent circuit elements: capacitor symbol, battery symbol, and switch symbol. There's 2 types of capacitors: electrolytic capacitors and variable capacitors. And the difference is electrolytic is used to store large amounts of charge at relatively low voltages, while variable capacitors are used for moderate to large amounts. And an example of a variable capacitor is commonly used in radio tuning circuits. Parallel versus series combinations. Voltage in a parallel combination is the same throughout all of the branches in the circuit. Charge is equal to the equivalent capacitance times the change in voltage, and the equivalent capacitance is equal to all of the capacitances summed up. In a series circuit, charge is the same throughout the circuit, while the change in voltage can differ by each individual charge over each charge's capacitance, and the change in voltage can be found by the sum of 1 over capacitance added up for each charge in the circuit. Energy stored in a charged capacitor. Since in a system, positive and electric charges are separated by 2 conductors and a capacitor, electric potential energy is stored in the system. In the system, work can be calculated after some derivations through the formula work is equal to charge squared over 2 times the capacitance. This equation appears as electric potential energy. Therefore, we can express the potential energy in a charged capacitor as the potential energy is equal to 1/2 times the capacitance times the change in voltage squared. These formulas apply to any capacitor regardless of geometry. This also states that as charge and potential difference increase, so does energy. A prime example of this is a portable defibrillator. Energy density. By plugging in the 2 formulas from the parallel plate capacitor slide into the previous slide's potential energy equation, we get the energy density. This translates to the energy density being proportional to 1/2 times epsilon naught, which is the permittivity of free space, times the square of the magnitude of the electric field at a given point. Capacitors with dielectrics. Dielectrics are defined as a non-conducting material such as rubber, glass, or wax paper. For capacitors that contain dielectrics, voltage and capacitance can be defined mathematically as a combination of these two formulas, simplified to capacitance is equal to K, where the dimensionless factor that represents the dielectric constant, dependent on the material of the dielectric, multiplied by the initial capacitance. For a parallel plate capacitor with a dielectric, capacitance is equal to this K constant times the permittivity of free space multiplied by area over distance. Dielectric strength. The maximum voltage that can be applied to a capacitor without causing a discharge depends on the dielectric strength, or maximum electric field of the dielectric. Where the magnitude of the electric field in the dielectric exceeds the dielectric strength, the insulating properties break down, and the dielectric begins to conduct. The advantages of a dielectric are there is an increase in capacitance, an increase in max operating voltage, and possible mechanical support between the plates, which allows the plates to be closer together without touching, thereby decreasing distance and increasing capacitance. Electric dipole and an electric field. The electric dipole moment can be defined as the vector p, or momentum, directed from the negative charge toward the positive charge along the line joining the charges together, and having magnitude of momentum is equal to 2 times the acceleration multiplied by the charge. Torque and potential energy can also be calculated, where torque is equal to the cross product between momentum and the electric field, while potential energy is equal to the dot product of the negative momentum dotted by the electric field. An atomic description of dielectrics. With a presence of a dielectric, electric field can be defined as E naught over K. Net electric field can be defined as E naught minus the induced electric field. A dielectric can be polarized by an external field regardless of whether the molecules in the dielectric are polar or nonpolar. The equation that shows that the charge density induced on the dielectric is less than the charge density on the plate shown is in this equation. Sigma induced is equal to K minus 1 over K multiplied by sigma. The surface charge induced on the conductor is equal in magnitude but opposite in sign to that on the plates, resulting in a net electric field of 0 in the conductor. Thank you all for watching. Hope you all have a nice day. Here's a summary